Right. Hello, everyone. Welcome to the AgentBuild community webinars. Today, we are going to talk about multi-agent systems. What I want you to take away from this session is try to understand the differences between a single agent and multi-agent and why multi-agent systems are important for enterprise workflows. Let me start with a simple example which you might relate to. Imagine you are building an AI agent for customer support, and it is smart. It knows all of the frequently asked questions that your customers are likely to ask, and it can summarize some of these conversations. It can provide answers. Maybe it can generate emails, and that's one agent. But soon you will see, especially in enterprises, business users will come and ask you to have it connect to the CRM system, connect to the Salesforce system. They will ask whether it can initiate a workflow that can refund the customer, or can it flag issues for compliance when certain keywords appear in the chat, right? And suddenly you see that this single smart agent that provides chatbot capabilities is juggling with many APIs, connecting to many different systems, trying to keep memory rules, and also trying to make sure that the approvals are correct. So soon it gets messy because it becomes too much for a single agent to deal with. And this is where you realize that this isn't a job for one agent. It's similar to where one human cannot do a lot of things together. A lot of these duties wouldn't be their skill set or expertise. Then you need teams of people coming together and doing certain activities. Just like humans specialize, delegate, and collaborate, we need these AI agents that can do the same. And this is where the multi-agent systems concept come in. Multi-agent systems wouldn't just respond to customer queries, as in this example, but they would also coordinate, they will specialize, and they will act together like a team, as I mentioned, like humans do. So in today's session, we will go beyond the buzzwords and we will unpack the architecture behind multi-agent systems. We will talk about the communication protocols, how different agents talk to each other. We'll look at the code and how enterprises can design reliable, auditable, and scalable multi-agent systems. So let's dive in. And let's start with a simple idea. As we have already established, that not single agent is not enough for enterprise workflows. Just like in a company, there are different roles like engineers, planners, analysts, all contributing towards the same goal. But because each of them have got their own skill set, their own perspective, and their own responsibility, the same applies to AI agents. Single agent systems often fall short when tasks are too complex, they are too dynamic, and they cannot really run in parallel. They either get overwhelmed or start producing flaky results because the logic gets too complex at one point. And that's where these multi-agent systems come in. Think about a system where an agent would take a user query and just analyze the intent and then pass it over to another agent that would search the internet for a given topic, find out relevant content from the internet for a given topic, and then hand it over to a newsletter writer agent who would then take all of these topics and create a newsletter in the language that the user wants, in the structure that the user wants, and things like that. While doing that, they use their specialized skills, they use the specialized tools that they need to do their job, and then pass over to the next agent when they have done their job. With this, if you imagine scaling, it becomes a lot more easier. It keeps logical boundaries of what different agents are doing. It's really easy for governance because you can keep track of which agents have got access to what systems, and it becomes a really modular system so that you can reuse some of these agents in different workflows given their skills. So in this session, we will explore how these multiple agents, each with a clear role, with a specialized function and autonomy, can work together to solve problems efficiently and reliably. Now, when we talk about multi-agent systems, there are three main concepts, if you like, that come to mind, and that would actually enable the success of enterprise workflows through multi-agent systems. The first one is specializations. Specialization means each agent focuses on specific task or skill set. Think of it like roles in a company. You wouldn't ask finance to go and write code, or a developer to negotiate a legal contract. In the same way, agents like a researcher, an executor, or a critique agent each do one thing and they do it well. Now, for enterprises, this improves accuracy, this improves auditability because they can separately audit each agent and what kind of tools they have got access to, and it simplifies governance, as I mentioned earlier, because each agent's scope is narrow and it is controlled. The second concept is coordination. Now, coordination means agents don't act in silos, they interact with each other, they hand off tasks, and they share context. This is where workflows come alive. A planner can break down a task, pass it to an executor agent, and have a critique agent to review the output and comment on the output. And all of this can be done without a human needing to oversee any handoff. And in enterprise systems, these kind of coordinations unlock multi-step processes across departments or systems, and they can then do it securely and reliably. The third pillar is autonomy. Autonomy means each agent can decide and act without being micromanaged. They can choose the tools that they have got access to, they can make the decisions that are right for doing their job, and they can recover from failure and keep moving. This leads to operational efficiency and scalability. You can run hundreds of workflows without needing 24 cross 7 human involvement, if you like. So agents become extensions of your own workforce, and they are no more just assistant. They are team members that can do certain tasks. So together, these pillars don't just describe how agents think, they define how businesses, enterprises scale AI with security and reliability in mind. Now that we have seen this mindset around why use multi-agent systems, let's look at in some real system architecture. So let's look at it from very high level, the 10,000 feet, right? At the center, you see one agent. For simplicity, I have kept one agent here, but consider it the agent layer, which would actually have a cluster of agents, like multiple agents in that layer. And they can have multiple roles, as I mentioned. It could be a researcher, another one could be an executor, the third one could be a critique, reviewer, etc. And we'll discuss some of these roles that agents take in the following slide. Now, these agents aren't just prompts, right? As we explored in our previous sessions, the component of agents are not just prompt. There are many other components within an agent that make the agent more than just an LLM. And these agents are task-oriented workers because you define their role, you define what sort of task they should be doing, and what sort of tools and APIs they have got access to, and then you enable them to collaborate in the agent layer. Now, these agents in a multi-agent system interact through a communication layer, like a message bus. We will talk about the different communication protocols later in another slide. But for now, just think that this communication layer is what enables agents to talk to each other, hand off tasks, or wait for input from another agent. Now, if you look at this diagram and start from the left-hand side, I wanted to describe some of these essential components for an agent to perform in a multi-agent system. The first one is the LLM pool. This is a shared pool of large language model instances. Think of it as a compute layer hosting different or giving access to different LLMs. For example, in AWS, we have got a service called Amazon Bedrock, which enables you to call APIs from different LLMs. And why do you need this kind of layer? Because in multi-agent systems, different agents might be handling different tasks. And if you think about it, different LLMs are good at doing different jobs. Certain LLMs are good at reasoning, certain LLMs are good at summarization. So in real enterprise workflows, what customers want to do is they want to have access to multiple models, and they want the ability for their agents to dynamically choose the models right for the job from a large language model pool. So that this is what the LLM pool does, and this is what it enables. It's like having a team of consultants and picking the right one for each problem. Then you can see the router. The router is a way of controlling and directing traffic. So if you think about it, it receives a message of a user or a user request. It inspects it, sometimes using an LLM to classify intent, and then hands it off. All right. So the router responsibility is to direct traffic. So if you think about it, it receives a message or a user request, it inspects it, and it sometimes uses LLM to classify intent and understand where a particular request should be routed to, which agent should be handling it. So if there are multiple agents, one handling customer complaints, another handling customer refunds, another one handling conversations with customer, depending on what request comes in, the router routes that. So if it's a refund request, the router will route it to the particular agent, and that's the job of the router. And then you have got the memories, tools, and APIs and actions, right? The external systems where the agent will access and do something like create a PDF and store somewhere and things like that. So the memories, tools, and external systems surround these agents. The memory memory stores facts, data. As we talked in our last webinar about memory and state management, where we talked about long-term memory and things like that. So that forms the memory component. With tools, the agent can do tool calling, access, do certain things like call the weather API to check weather details and things like that. Again, we covered it in our previous webinar around tool callings. And then obviously you have got data stores and actions and things like that. And it's important that the thing here is to understand that this system is not a hierarchical system, right? It's a network of agents that work together depending on what needs to be done. And obviously there are certain communication protocols and coordination patterns that you can achieve using multi-agent systems, which we will be covering in the coming slides. So what kind of roles we normally see or we can normally assign to our agents? One of these could be researcher agents, so where it gathers external knowledge, searches the internet or searches internal documents, it distills raw data into usable information and then brings that back. So that's one kind of agent that you can think about in multi-agent systems. The other one would be a planner agent, where it would break down high-level goals into steps, understand what needs to be done, and then assign those different smaller problems to other agents through the routing capability. Then there would be the executor agent, who would be accessing tools, taking actions, making API calls, modifying data, and doing what needs to be done in terms of executing certain tasks. Then you would see this critique agent, which would look at results or tasks done by other agents, check the output for accuracy. It will check the output for tone, for compliance, for security, make sure that no PII is getting leaked and things like that. That's the job of the critique agent. And there would be a messenger agent, which would handle communication, like sending a notification via email or sending a notification to Slack, or creating a PDF and sending it to someone and things like that. So the messenger is responsible for formatting results and delivering them via different communication channels. And having this mindset while you design multi-agent system is really important, because when you break down a use case from your business users and try to understand what kind of workflow you should be building, at that point you think about what kind of agent would do the research part. You need to understand there needs to be an agent that can do the planning, there needs to be an agent that will be doing the execution, critiquing, sending messages and things like that. And this kind of modularity in the design is really powerful, because it then mirrors real world workflows. You wouldn't ask a developer to quality test their own code, right? Or a planner to execute every API call. When you assign tools or roles, like giving the executor access to billing APIs, but you don't give the critique agent access to this billing API, you both from the governance side, you get clarity on who should have access to what, and then you can also apply security models to make your workflows more robust and secure. And now that you understand these roles and you've got these roles, let's check how these agents talk to each other. Now, agents speak JSON, right? Why? Because structured communication is machine readable, so machines can read them. They are auditable, it's easier to audit. You can programmatically create reports and audits and stuff like that. And they are debuggable, so you can actually go and debug if there are problems. Now, a message might have a task ID, a from and to field, where the message is coming from, who the message should be going to, what type of message it is. Is it an instruction? Is it a query? Is it a result from some other agent? And then a body, like the actual data. And this schema is the backbone of your agentic system's observability. So think from the perspective of being able to understand what these agents are doing. What are the multi-agent systems doing? What are each agent within the multi-agent system doing? And in order to understand that, in order to monitor that, you need this kind of information. You need access to that so that if anything goes wrong, you can go back and detect what went wrong, where it went wrong, which agent failed, and things like that. Every tool call, every write in the memory, or agent responding to anything can be traced through the observability layer. And that's critical for enterprise use where compliance, audits, and reproducibility, they matter, right? They will always keep coming up. So now that you understand that we have structured messages between these agents, how they communicate, let's look at how they move across different communication topologies. So now you see the structure of the message. Now we'll see what are the different ways of passing this message. What are the different protocols that the agents take in order to communicate with each other. There are three main that come up across different multi-agent systems. The first one is broadcast. The broadcast topology is, think about it as every agent is hearing everything, basically. So imagine a Slack channel. If you are in a Slack channel, in a group, in a Slack, you can, all the members of the Slack channel can look at each and every message, right? Similar way, here, all the agents are listening. So any message is visible to each and every agent in that multi-agent workflow. So whenever one agent has an update, maybe a tool call or a result or a plan, it posts that message to the event bus, which is shared across all other agents, and all other agents can see that event. And so why is this relevant in enterprise use cases? Think about a use case like fraud detection system. So there might be a signal detection agent which might broadcast. Let's say there has been a fraud. So a detection agent detects the fraud and it broadcasts that, hey, this event, this credit card transaction has got is likely a fraud, and it posts that message in the event bus, which is visible by all other agents. So a risk scorer agent can immediately take that and score a risk. A note taker agent can immediately take notes about that event. A human escalation agent can escalate directly to a human in the loop, so that they can take that event and research more about that, and that happens immediately. And this is great for this kind of dynamic collaboration and discovery. And all this also means that agents don't need to know who else exists in the pipeline, in the system. Agents just need to go and talk to the event bus, and everyone else reads the event bus and takes the details. It's easy to add new agents without breaking the things. So you don't need to do a lot of engineering to add a new agent in the whole workflow. However, it can really get really get noisy, because all of these agents are posting what they are doing, the messages, the results into one communication layer, which means that the other agents need to trace the right message that is relevant to them to do their task. So because it is shared, as a disadvantage, it can get noisy especially when there are many agents. Think about hundreds of agents or even 20 plus, 30 plus agents. It gets harder to trace for these agents to go to the correct message. Then we can talk about the direct messaging protocol or topology, where basically agent A talks to agent B, and sometimes so they directly communicate, and sometimes there might be a deterministic routing between them. And what does it mean is that in direct messages, no other agents can see these messages. So obviously there's privacy in the messages passed between these agents. Agent A sends a task to agent B. It's clean, it's intentional, and highly efficient, especially in linear workflows where you have got a workflow where one agent should talk to another, should talk to number three, should talk to four, and none of them talk to others. So they're always talking to one agent. In this kind of use cases, this becomes really beneficial. Think about a customer onboarding pipeline. So there might be a form, the customer fills up the form to sign up somewhere. The form extractor agent would send all of the structured data that the customer has entered to the validator agent. The validator agent would validate the data, make sure that it's all correct, and then send it to a database writer agent. And the database writer agent will take all of this and write into the database, and finally inform another notifier agent that this has been done. So this becomes a lot more linear, precise, and efficient workflow and way of communicating between agents. It's easy to follow because it's basically a chain of execution, and it's ideal for sequential pipeline type tasks. The thing with this is it, in terms of if you think about challenges with this kind of topologies, is it requires some sort of routing because you must know, as in when I say you, the multi-agent system, the agents must know which agent handles what, and then they are tightly coupled, because now if you had to insert, let's say you have to create another agent and that agent comes in between these two agents, then you have to re-engineer the communication topology, right? So you have to change a lot of things. So because these are tightly coupled, so that means that it adds a lot more work in terms of if you wanted to add new agents in the workflow. Then the third is the blackboard communication approach. The blackboard pattern is, think of a as the name suggests, it's basically a blackboard where you write stuff and others can read. The way it works is it's basically think about it as a shared space. It can be a memory, it can be a shared memory or a space where a file where agents can write. This one is a bit more abstract, but it can be really powerful. Think of it as a, how to say, as a notepad, right? Or think of it as a Kanban board where agents write messages. Like one agent can go and write, customer has asked about invoice refund, right? And the other agent read that board, filter the tasks based on their roles, and act. So because they are written, the other agents can basically filter them based on what they are supposed to do. So they don't go and look into each and every message like in the first one, but they basically go and filter out the messages that are relevant to them, and they just look at them. Think about an internal help desk agent system. So in an internal help desk agent system, there would be an agent that would post new customer queries reading at email inboxes, and they will post customer queries to the Blackboard. And then the finance agent or a tech agent or an HR agent or any other agent who monitor that Blackboard, they will filter customer queries relevant to their department and then pick those tasks up and act on them. And this creates a loosely coupled system because now agents are not tied to each other in direct messages, and they can scale horizontally because they are loosely coupled. They can scale horizontally. You can add more agents without bothering about re-engineering communication channels and stuff like that. And also they can come and go without breaking the flow, right? However, it needs careful task assignment logic to avoid duplication. So that means that whenever these agents read what kind of task they will be doing, you have to code the logic in the proper way so that there is no duplication. And then it also means because an agent is writing to a shared space and then the other agents are going and filtering through those messages and reading the appropriate message for their task, it would add latency to the whole workflow. Means they will be spending some time doing these tasks in terms of polling and monitoring and all of those things. So this will add a bit more latency in the workflow. So as you can see, in multi-agent systems, there are different ways of communicating between agents. These are different topologies that you can think about. And the message here is that there are trade-offs. Each of them have got their advantages and disadvantages. And as a builder, your job is to identify the right pattern for the right use case. So it's not that they will not apply anywhere or they apply everywhere. Each of them would apply in different use cases. Like I said, I was giving the examples what I was explaining. But that's what you need to keep in mind. Now, let's talk about coordination patterns, like how these multi-agent systems, how multiple agents can coordinate in different patterns within a multi-agent workflow. The most basic form is the sequential. One agent hands off to next. This works great when the workflow is strict and the order matters because it needs to be sequential. Like in a document review or communication pipelines, you need the sequence to be there. So it's just straight. One agent does the task, hand off to another one, right? That's sequential, simple. Now, if you want speed, you have to choose patterns like parallel fan out, right? Where say you are summarizing 10 legal documents. Now, if you did it in a sequential pattern, then you have to do one document at one time. But if you went to a parallel pattern, then you can do 10 documents in parallel. So there will be a coordinator agent or an orchestrator, and then you will have all of these agents which will do the legal review run together in different pipelines as shown here, right? So each of them tackle things in parallel, and that means you gain performance. That means you can review 10 legal documents together, and that makes the whole process faster. Then there is this broadcast pattern, which we already talked about in the communication protocol, like posting in a Slack channel. One agent pushes a message, all the other agents can look at it and react depending on who needs to react. It's powerful, but again, as I said, it can get noisy very fast, especially with 10 plus, 15, 20 plus events, right? 20 plus agents. Now, to reduce this noise, you can go with the direct messaging that I was explaining earlier. One agent sends exactly to what the other agent needs. No more, no less. It's just direct message. Sometimes you might need a router to decide which agent the message should go to. Otherwise, it's pretty simple direct messaging protocol. The other one is the blackboard. Again, what we were just talking about in the previous slide. It's a classic approach. Agents don't talk to each other directly. There is some sort of memory or an object that can store data. So instead, all of these agents write their observations or plans on the shared space. The others pick up depending on what's relevant to them. It's like a bulletin board, right? And it's great for loosely coupled systems, right? But then again, there are trade-offs that I was talking about, that it might add some latency to the workflow. And finally, the hierarchical is very common. You'll see in multi-agent systems where there is a supervisor agent. It takes the lead, it delegates tasks, it monitors progresses, it makes sure the things are safe and secure. Sometimes it can take the critique role as well. It's like a manager of a team, right? Who oversees the team's goals and the plans and makes sure that everyone is executing on what they should be executing. Again, each pattern has got their trade-off in terms of latency, in terms of complexity and observability. The real question is what's right for the use case. That's what you should always think about. What's the right pattern for this particular use case? In the next slide, I will show you how some of these map into actual orchestration frameworks. So far, we have talked about agents as individual roles, but let's step back and ask, how do you manage 5 agents, 10 agents, or more than that, right? Even 100 agents when they are talking to multiple tools, they're talking to multiple systems, multiple databases, coordinating with each other and maintaining memory and context while doing that. In these scenarios, you need a multi-agent orchestrator, a runtime system that wires these agents together, defines workflows and handles communication, handles execution order, and handles fault tolerance. If you see in the middle, this rectangle, I have listed some of the popular orchestrators that you will see in the market, but obviously there's a lot more. It's not the complete list, obviously. But LangChain is a very common one. QAI is a common one. N8N is a low-code, no-code orchestrator. And in AWS, we've got Amazon Bedrock multi-agent collaborator, which provides orchestration as well. Now, if you think about each agent, a planner, a critic, an executor, they might specialize in something different. And the job of the orchestrator is to make sure they collaborate in a defined way. They do the proper handovers, so handoffs, and then the orchestrator can implement the different patterns that we are talking about. So if sequential, orchestrator can make sure that the handoffs are sequential. If you need parallel, the orchestrator can make sure that the handoffs are parallel. And why does this matter to enterprises? Because agents at scale, when they run, is got to get access to all of these systems and tools and doing different tasks. They require some sort of structure to operate in a workflow. And without this orchestration layer, you end up with a mess of APIs, of retries, of memory bugs, and everything. So with an orchestrator, you get clear workflows, you can structure workflows, you get the observability that you need through the orchestrator, and you get recoverability. So when something fails, the orchestration knows and it can have it retry things and things like that, right? So orchestration is what makes agents powerful. In production grade systems, you need an orchestrator to implement multi-agent workflows. Now, I wanted to show you a quick demo on a multi-agent system, on especially when you write code, how it looks like. So what I wanted to show you is, you don't have to read the code or anything. This is an example. So this is a GitHub repository from QAI. You can find it on QAI GitHub. I have cloned it here. I want you to focus on this part, the screenplay writer, right? There are many use cases that they have applied here as examples on how you can build multi-agent or systems or workflows. There's one for job posting, there's one for trip planning and things like that. The one I wanted to show you, because it's a very simple one and it's very easy to understand, is the screenplay writer. Now, the use case here is given a text, given, let's say, an essay or a news piece of news and things like that, it is asking for the agents to convert it to a screenplay. So a screenplay, create a scene where there is a dialogue exchange and there are different characters and they talk to each other, right? So it's basically give it a script and it converts it to a screenplay. So it's really beneficial for filmmakers or writers who basically write a story and give it to and then they give it to this particular system, and it creates it rewrites the writing into screenplay, right? It creates the scenes and the screenplay. So that's what it does basically. Now, if you had to build such a system using Q.AI, you need different components in there. So one of the main components is obviously the agents, right? So you need to define the agents. So if you see here in the code, we have defined different agents, right? So the spam filter is one agent. What is the role of the agent? We have defined a spam filter. What is the goal of the agent? Decide whether a text is spam or not. So one of the tasks that this workflow does is, when the text is fed as input, it looks at the text and sees whether there are anything that would be considered as spam. So it filters those out, right? There might be vulgar language, there might be advertisements and malicious links and things like that. So you define the agent, you give it a role, you give it a goal, and you give it a backstory so that it knows what it needs to do. So it says, you are an expert spam filter with years of experience. You detest advertisement, newsletters, and vulgar language. It's a very short prompt. You can go larger and be very specific with these prompts here. And then see, there's another one called analyst agent. The analyst agent role is to analyze. The goal is to, you will distill all arguments from all discussion members, identify who said that. You can record what they said as long as the main discussion points remain. And then the backstory is, you're an expert discussion analyst. So the analyst is basically, it looks at the discussion fed through the text, and it divides the discussion, tries to make out who says what in that discussion, and then assigns them that way. Then there is this script writer agent. whose role is scriptwriter. The goal is to turn a conversation into a movie script. Only write the dialogue parts. Don't start the sentence with an action. Do not specify situational description, blah, right? So it's basically a prompt that describes what it should be doing and what is the backstory. Now, if you see in this whole thing, there are different agents that have been described. So the spam filter, analyst, scriptwriter, formatter, and the scorer. So the scorer is basically goes and assess. It takes the role of a critique agent, right? So it scores the quality of the screenplay that the scriptwriter has written based on the text provided. So you see each of these have got their own roles and they have got their own backstory. So this one component that you need to build while building this multi-agent system is the agents, right? Define the agents. The other thing that you need to define is the task. So you define what these agents are exactly going to do in this multi-agent workflow, and you do that through prompts. And that's why prompts are really important, and writing good prompts become really important in building agentic systems and also multi-agent workflows. So if you see in tasks, there are different tasks. The way to describe the task is you can give it any name, to be honest, but here they have given task 0. The description of the task is, so the first task is read the news post. If it contains vulgar language, reply with stop. If not, and if it is a spam, reply with stop, right? So it's basically the first task is to go through the text and detect whether it's spam or not, and you immediately know which agent should be handling that. So a task has been defined for this agentic workflow, and the task will be assigned to the spam filter agent because the spam filter agent is built to do this kind of activities. The second task is analyze in much detail the following discussion, and then you provide a discussion parameter, and then the user can input the discussion, and because this is a parameter, we in double braces, it will take the input parameter in here, and then you can say the expected output. So you can define it, what is the expected output of this task. The expected output of this task is a detailed analysis of the discussion, identifying who said what, and rewarding and maintaining the main discussion. Now this task will be assigned to the analyzer agent, and so on and so forth. There are many other tasks that have been described, and each of these tasks would be assigned to the agent that it should go to. Now, once you have defined the agents, once you have defined the tasks, how do you stitch them together? In the main file, so this is a Python, in the main file, and again, you don't have to go through each of these right now. What this part does is it basically makes calls to these files. So the config, the agents.yaml file and task.yaml file, it creates this connection here so that the code on this page can read those files. And then there is an environment variable where we have given the OpenAI API key because it will make calls to the GPT language model. So that's the LLM. And we have loaded that API key here in load.environment, right? Now, the important part in this code is where you define these agents. So you have created the text, you have written what this agent should be doing, what's their role, what's their goal, what's the backstory. And this is where you use QAI's method, agent method, to create the agents, right? And so you say agent config, spam filter, this name matches with the name of the agent's YAML here. So it takes that from there. Spam filter, allow delegation equal to false verb. There are different arguments that you can provide, right? So the verbose equal to true means that it will log everything. If you put it false, then it will not actually log a lot of this stuff. So now you see we have defined each of these agents here, the spam filter agent, the analyst agent, and all of these point to those names that we have described in the agent config file. So now at this part, all of the agents are defined. So think about it that the agents have been created. Now we provide the discussion. So remember we had double braces discussion. So this is where we provide the input. Now in this code, for simplicity, they have given this sample, but you can convert this code in a way that the user can insert the discussion as a text or a file somewhere like in a chat bot or things like that, right? So that can be done. But over here for simplicity, we have provided the discussion, hard-coded it inside the code itself. Then comes the tasks. Now we define the tasks. We had all the text, everything defined. And so the details are there in the task.yaml. Now what we are doing is we are creating task 0 with the task method, we have created the task. So we're saying that the task config is task description. These are being picked up from the config file inside here. Picked up from the config file over here. So you have a task description, expected output, and that's what it's doing here. It's creating the tasks and assigning that task to the particular agent. So you see what it does. Task one was to analyze these events, the discussion. As you see, task one here is to analyze in much detail the following. So it needs to go to the analyzer agent. So it has assigned this task to the analyst agent over here. So it's agent equal to analyst, right? And similarly, it defines all of the other tasks and then assigns them to the different agents. So this one goes to scriptwriter, this one goes to formatter, and then at the end, this is the orchestrator method. This is crew.ai's orchestration method. What it does, it says, hey crew, we have got this agents crew, we have got these 3 different agents, we have got these 3 different tasks that need to be done. Log everything that you are doing. So crew will let you know what tasks are being worked on, what is set to 1, 2, 3, and different logging levels, right? And then it says process them in sequential method. So crew.ai provides this method called process, where you can then define different ways, different coordination patterns. So you can do sequential, you can do parallel, and they have got some of the more other workflow patterns. So now this becomes a sequential workflow with different tasks and different agents. So everything is defined, and then you just kick it off. So you say result equal to crew.kickoff. Now crew basically goes and kicks it off, and then results comes out, then it stores. Now let me run this code and show you how it works in practice. So if I run this code, let me just pull it up a bit. So it started from here. So you see, let me just scroll up, started from here. Now that we have run the code, you can see what has happened. So crew execution started. So it's logging everything in variables, right? Then it says executing start task. So it has started the agent analyze agent. It says the task is to analyze in much details, and you can see that it has taken it from what we have defined in the file. Then it takes the discussion that we have provided here, this passage, right? And what it does is it analyzes this passage, and it says that in this discussion, multiple members contributed various perspectives on the topic at hand, and then it analyzed and tried to point out which member said what. So it's like member A says this, member B says, member C says this, etc. Then it says completes analysis. Then it goes to the scriptwriter agent. Then it kicks off the scriptwriter agent. The scriptwriter agent's task is to create a dialogue-heavy screenplay. So it will write the script from that passage. So the analyzer agent hands over to scriptwriter agent. Now the scriptwriter agent starts to make that script, and it has come up with the final answer of creating that script. Then the scriptwriter agent completes. Once it is completed, it goes on and hands it over to the formatter agent. Now the formatter agent's task is to take those lines that the scriptwriter agent has put and format that into a screenplay format, right? So person 1 says this, person 2 says that way it formats that. So you see formatter agent says person 1, first line in text from person 1, person 2 from person 2, person 1. So it's a dialogue, right? So between 2 persons. So that's what it is formatting it to. Once it has completed it, it has come back with this formatted answer, where it says the final answer is member B says this, and finally it throws this answer, right? So then it says crew execution completed. It has run all of those 3 agents and come up with an answer. Now you can take this output and throw it to a web interface, a PDF file, send it over Slack, whatever, depending on what kind of agent you use and what type of task. So we could actually improve this by adding another agent that would have access to, let's say, Slack. And it would take this message, create it into a Word file, a PDF file, and act as a messenger to send it to Slack as a message or an email as a message, right? So we can add more agents to this. And the way we do it is we'd go to agents, create another agent saying messenger agent, give goal, that your goal is to create this and do that, give a backstory, we'll add a task, we'll go over here, and then let me minimize it a bit. And then we will define the agent over here, like email sender agent or whatever, and then write a task. And then in the crew here, we will add that fourth agent at the fourth task, and then it will go and pick that up when we kick it off as a step 4. It will go and do all of these things, right? So that's how it works when you work with QAI. It's much similar. If you understand one of these workflows or one of these tools, you can easily map your knowledge to others. So it's very easy to do that. And then there's this NA10, which is low code, no code, where you can drag and drop stuff. That is a really good tool as well. If you wanted to, you can try that one. So now that you have seen a quick demo on how multi-agent system work, I wanted to show you how actually these things work in practice, right? So how enterprises would end up using this kind of workflows. Now, this example is of a smart fleet management system where think about companies who have got huge amount of fleet, right? So as in many vehicles around in the company where they use these vehicles to either deliver products like Amazon.com, right? So Amazon.com has got so many vehicles that deliver products. And one of the problems that they face in terms of fleet management is that vehicles going out of order, something goes wrong, and if they cannot actually pre-plan or understand what's wrong with the vehicle or even predict that something is going to get wrong with the vehicle, then if something goes wrong on the day of delivery, then they have to do a lot of rescheduling and stuff like that. So that's a very big problem. And this kind of workflow can solve these problems where there are sensors fitted in the vehicle and the sensors can detect that something is going wrong in the vehicle. So let's say the oil pressure drops down. The sensor detects that. It sends an event. The event is grabbed by an event bus, and that event is sent to an anomaly detection agent. Now remember, the anomaly detection agent here is not actually an LLM agent. It is an ML, traditional ML agent, where it's just an anomaly detection machine learning model. And it detects anomaly, and this creates an event that kicks off the orchestration layer, right? So that when an anomaly is detected, it says, oh, there's something wrong with this vehicle. Let's kick off the orchestration layer. And this is where the orchestration layer comes in and kicks off the supervisor agent. Now this is a this is a hierarchical pattern that we talked about. There is a supervisor which supervises what all of the other agents does, and then it maintains state somewhere. So what the supervisor does is it says, we got an anomaly. By the way, this orchestration layer, you can use any one of them. It's just an option, that we have shown here, but you can use any one of them. So once that is kicked off, the supervisor agent tracks there is an anomaly. We have to do something about it. First, it goes and registers this anomaly in a database so that it's there somewhere stored. And then it goes and calls the maintenance planner agent. So it says, hey, we have got a fault in vehicle number. The anomaly is in the oil pressure that dropped. Maintenance planner picks that up. It goes and looks into its database and then schedules and updates stuff. So maintenance planner say, oh, so the oil pressure dropped as per our database records. When oil pressure drops, these are the steps that we should take. We need to schedule and task for someone to come and repair it. And in that process, it realizes that we might need to buy some parts or procure some parts, because if we need to change the oil filter, we'll need a new oil filter. So the supervisor agent goes and kicks off the procurement agent. The procurement agent raises a request for procurement saying that, hey, we need to buy a part, and it sends a message somewhere to someone who's responsible for that. So it places the orders, notifying the stakeholders that this part needs to be bought. And then if you imagine in real world, this will take at least 1-2 days, right? So it's not instant. It will take 1 or 2 days for that part to arrive, and then it would also take few days to get the technician's appointment to bring the technician to service that vehicle, right? So that means in this kind of workflows, there needs to be some sort of state management. What that means is that you cannot really keep this workflow running for 2-3 days, right? So at one point it will pause, it will turn off, but it will store some checkpoint in a database so that when a technician comes in and that technician gets that part that was ordered and the technician scans that part, let's say there is a QR code, or technician starts his or her job. When technician says, okay, I'm going to start my job, that event on the system will trigger this workflow again, and the workflow will be picked up from that state that it was last executed because it's stored in the database. Then the workflow says, now we kicked off again. The technician has arrived. He or she has got the part that was ordered. They are servicing the vehicle. In that process, this agent will also guide the technician with manuals and documents in terms of which vehicle it is, what kind of part it is, how do you do it. All of the instructions will come up on the technician screen. The agent will help them. And once the technician has done the job, they will report it back to the supervisor agent that we have done the job. It will go back and update the database that, okay, your job completed, everything works fine. Then it can again go back to the maintenance planner agent and say, plan the schedule for this vehicle. This vehicle is on road again. It's ready to go on road again. So do whatever you want to do in terms of scheduling its delivery and things like that, right? And in that process, you put guardrails everywhere, make sure that no sensitive information is passed out. For example, the procurement agent might be using some card details of the company card to order parts. In that case, you need to make sure that the card details are not leaked somewhere. It's all secure and safe and things like that, right? So if you think about it, in actual enterprise workflows, this is how things will work, right? So it's not one sequential workflow and then it's done. Yeah, there might be use cases for that, but in complex use cases like this, you will have agents working, maintaining state, stopping somewhere, and after 2 days kicking off from somewhere else. And this is where it's really important to have this orchestration layer. It's also important to understand that not every problem would need an LLM agent. There will be ML agents or even rule-based systems, or even systems and tools that enterprises are already using, right? So you cannot really replace them. So they will also play a part into these workflows to deliver the whole business outcome, right? Hopefully this is clear. And if you try to map this across other use cases that you in your organization or in your or maybe a customer you're working with, think about this kind of patterns and what is the use case. Does it actually, what kind of multi-agent pattern, what kind of coordination you should be putting, and what kind of tools and systems you should be working, it will be connecting to, it will be working with. Does it need to maintain state, store its state somewhere, and things like that. So there's a lot of thinking going behind it. Agentic systems are not magic. It's pure system architecture, and you have to understand the use case and the business outcome needed to design these kind of systems. Now that we have seen all of this stuff, let's look into the future a bit. What's coming up in the multi-agent system domain? We have seen single agents with long looping planes. We have seen orchestrated teams. We have talked about how you define roles and stuff like that. But what if instead of creating and pre-wiring agents and roles, you let agents to create new agents on the fly, right? So in our previous example, what if the supervisor agent decided that we need to buy a part, and in the runtime created the procurement agent rather than you creating this procurement agent upfront during the design time, right? So the supervisor agent says, we need a procurement agent right now, but we do not need to buy parts and each and every repair, right? Not each and every repair needs to buy something new. It can be a normal repair where nothing needs to be bought. So in those cases, supervisor agent could go and actually on the fly create a procurement agent and then retire that procurement agent when it's no more needed, right? So this is the concept of where we are getting into with multi-agent systems. And this isn't science fiction, by the way. Tools like LangGraph, there's another tool called temporal.io. They are already enabling this kind of runtime orchestration. So I've given you the example. And if you look at it, this is what it's going to do. You have got a parent agent. You have got a number of other agents that do different tasks. And the parent agents basically in runtime create these agents. And when this agent's job is done, it is no more required. They retire them, right? So these agents are, so it saves costs as well. So it's going more around usage patterns, right? Rather than just having everything designed upfront. And if you think about systems where you will need hundreds of agents to deliver some complex tasks, I'm pretty sure a good number of them will be using this kind of pattern where they will just be created when needed and then disposed of or retired when they are not needed, and then created later on again when this kind of requirement arises. So this is where we're moving to. It's a really interesting space, and we can maybe in future sessions explore more about it. With that, I would like to pose a challenge for you. As I explained with QAI, you can use any of the other tools like LangChain or N8N and design your first agent team, so multi-agent system. Choose a real-world enterprise scenario like the one below. Pick up a simple one, not the one that I showed earlier. A simple one like a marketing intelligence bot, marketing ops, so where you could track a competitor pricing and sentiment from website. So you have an agent that will scrape a website data, and it pulls product data and reviews from websites. You can have a summarizer agent that summarizes those insights into a report, detects sentiment and stuff like that, and then a notifier agent that sends alert to an email or a Slack, right? So 3 agents with a goal of tracking competitor pricing and sentiment on a weekly basis. Try to build that. You can use QAI or N8N on LangChain, whichever is easier, and then create a short demo, a README file explaining the agent roles, the tools they use, the coordination pattern that you have chosen to use, and a simple demo video showing your agent in action, and then share it on Discord. With that, thank you very much for your time today.